Today is the first class after the Idul Adha vacation. So we're gonna pick up the parachutist graph. In our last class, just to begin with the concept of parachutist graph, I talked a little bit about what do we mean by GPE and what do we mean by KE. We talked about these two variables. GPE of a certain object is given by the expression mgh. M is the mass of the object, G is the gravitational field strength or gravitational acceleration, H is the height of the object from a certain designated zero level. This choice of zero level is very important because the total amount of GP can be different for different perspective level of the H equals to 0. Kinetic energy of the object is the energy that an object has by virtue of its motion. The expression for kinetic energy is given by half mv square. It's a very simple formula. Half is a constant which comes up from the expression during the derivation process, which I am not showing you right now. Just bear with me for the formula. M is the mass of the object, where V is the instantaneous speed or velocity, could say either, of the object. So half mv square gives you the total kinetic energy content of an object at any point of time. The motion graph for the parachutist looks somewhat like this. So the idea is very simple. We have a high flying aircraft. Let's say it's a helicopter, or we're considering a helicopter because we're only gonna observe the motion of the parachutist in a vertical direction. So only in a vertical direction. So let's say here we have a very high flying aircraft from which a parachutist takes a jump. So here's a parachutist and he's about to take the jump. So what's going to happen from the instance that he takes the jump of the helicopter, which is currently maintaining a constant level at a high level of atmosphere. So let's say that is U equals to 0. And as he falls down, what are the scenarios that happen throughout his motion? That's what we are going to see today. So the graph essentially looks somewhat like this. I'm going to draw up the graph first and then take you to different parts in terms of motion. We're going to talk about displacement, velocity, acceleration, also the energy change for individual parts of the graph as well. So this is the velocity time graph, or you can also say speed time graph. The reason we can use either of these terms is because throughout the entire journey of this parachutist, no matter what he does, he is always going to fall downwards. This motion is always downward velocity. This is very important. Some of us might feel like that. Well, when the parachute gets opened, the person actually starts to go upwards. That is not at all true. That is a problem that we have due to our perspective. I'm going to explain that in due time. Let me just start with the graph. So the graph somewhat looks like this. So for convenience, we're going to divide this into multiple different segments. Let's say we have a straight line part over here for the graph, which is visibly straight. Let's say it's up to this point, let's say OA. And then from A, we have a visible part where it is losing gradient. It is becoming more slanted or more horizontal. That is part AB. And then we have the BC segment where we have a constant velocity. C is a point of time when the parachute is getting opened. So we suddenly have a very, very large upward force because of the increase of surface area. And then C is the decrease of the velocity with decreasing deceleration. So I'm going to talk about what happens over this at this point in detail. And then let's say after the parachute is open, within a short time, the person once again reaches terminal velocity. This graph actually should be much more shorter in time, but I just made it wider to give a bit of an understanding that this would be a graph of decreasing gradient. And let's say this is the point where the second terminal velocity is reached, and this is the final velocity. This is the point of time where the person actually reaches the ground. So the velocity, instantaneous velocity, becomes 0. So first of all, let me take you over a couple of misconceptions that students sometimes have. Not all of them have, just because I want to play safe. The first thing that I want all of you to understand is that whenever any object experiences zero resultant force, this does not only mean that object is stationary. A moving object can also experience resultant zero force. That's also very much possible. what's the most common example that I could possibly give you that a moving object can experience zero resultant force? Here's the case. Uh, to give you an idea of this thing, I'm gonna take a bit of discussion for the air resistance. So if we go for air resistance, what is basically air resistance? Air resistance is very much similar is a very simple topic. This is actually a type of resistive force that an object experiences whenever it passes through air. This discussion about air resistance is equally applicable whenever we are going through some other fluid medium. For example, if you consider water or glycerin or some other type of oil. So whenever you have a fluid medium, you can pretty much use the discussion that we are about to have right now. The idea of air resistance is very simple. The idea is that if we have an object, for the sake of understanding, let's draw a let's say cuboid object. If you have an object that is moving through atmosphere, where we have the atmospheric particles right over here, to move past through the atmosphere, it has to push the atmospheric particles out of its path and make its own way. So in the process of moving forward, it will collide with each individual air particles that is in its path. So this object is going to apply some force on these air particles in the forward direction and produce a high pressure region that's going to practically swap out the air particles out of its path. And by Newton's third law, whenever the collisions will happen, the air particles will also apply an equal amount of opposite force onto the body as well. I'm now drawing this arrow over here because I am supposed to actually move this object from left to right, which I cannot do for this Microsoft whiteboard. Would have been better if we are using some sort of animation. No, Kasi, you don't have to draw the graph. Just keep listening, and if you have any question, you ask me. That would be great. So these two forces should be exactly in the same position. So whenever the object collides with any of the air particles, they experience force. The object pushes the air particles in the forward direction by Newton's third law. Before the air particle move away, the air particle pushes the object in the backward direction. I'm using the term air particle, not preferably molecule, because air is not always essentially made up with air molecules. We have air molecules, essentially nitrogen, carbon dioxide, oxygen, and other neutral gases can be also present. Some sulfur dioxide, nitrogen dioxide in very small quantity that can be there. But air is also made up with H2O molecules, which is vapor, and it is also made up with dust particles, which in many cases are not so visible because they're very fine and very, very small. So using the term air particle actually encompasses all of them in a generic name, that air particles, everything that air is made up with. That's why I'm using the term particle, not preferably molecules. In many cases, you can also write molecules for your description, but particle, writing air particle whenever you're trying to mean the whole atmosphere is a much safer term. That's how I'm going to put it. So each of the collision that the object will make with the air particles is going to result in some backward force. Now, individual collision, one collision that the object makes with one air particle would be very small. But whenever the object keeps on moving through atmosphere, it actually keeps on colliding with a large number of air particles. Let me give you a simple idea. I can use a bit more space over here, maybe. Let me give you a simple idea. Let's say if the object is moving at, let's say, 10 meters per second speed, and if I try to draw a cylindrical space or a cuboid volume of space, which has a length of, let's say, 10 meters, it means within 1 second amount of time, this object is going to cover through this much cuboid shaped air volume. Now you might wonder, where is the cuboid? I don't see a cuboid. I'm actually trying to draw the side view of the whole observation. So actually the volume is behind the screen. You are seeing the side view, you're seeing the two-dimensional representation of a three-dimensional happening. That's why you're only seeing a long rectangle that has a length of 10 meters. So within 1 second of time, the object is going to travel through this much distance, and it's going to collide with all the air particles which exist over here. And if you sum up all of those backward forces, if you sum up all of those backward forces that the object experiences because of the collisions, and those resultant forces, you add up all those, is basically the total amount of resistive force the object is going to experience over 1 second of time. That's a very simple understanding of air resistance. Now, second thing, if the object had double the speed, try to understand this part. If the object had double the speed, let's say if the object was moving at maybe 20 meters per second, then what's going to happen in that scenario? Let me choose a bit bigger thickness. Yeah. In that scenario, within that same 1 second duration of time, the object would have covered double the length of air. So it would have covered 10 meters and another 10 meters within exactly 1 second. So the number of particles it would have collided would simply become double. That's only half of the story. The other half of the story is whenever the collision is happening at 10 meters per second, the force involved for each individual collision would be small. Whenever the collision is happening at 20 meters per second, the force involved would be essentially double. Because you're I shouldn't say it would be exactly double, because saying it double would require me to give you some mathematical proof. Let's just say that the force would become significantly bigger, not necessarily double. It would be around double. Let's say the collision force, each individual collision force will become bigger. So you have two factors in play here. Whenever the object is moving at double speed, you have collision with double number of particles, and each individual collision is giving up a much bigger amount of force. So the total amount of air resistance would be simply higher, significantly higher. Why am I telling you this? Because you have to understand that this resistive force that the object will experience in the backward direction, which you are calling air resistance, it is not directly proportional to speed. No, it is proportional to some exponential of speed. So as object goes at higher speed, air resistance slowly starts to soar and becomes bigger and bigger at an exponential rate. That's why at lower speed, the effect of air resistance is not so much even understandable. I mean, if you're just making a walk, you don't even feel air resistance. But at the moment you start to run, you actually feel the air resistance. If you are in a car, if you put out your head, which you shouldn't unless the is safe in an open space or something like that, or if you put out your hand, you would feel the air resistance. The faster the object would move, the more air resistance you're going to experience, and that is a representation that how the resistance actually interacts. And there is and there is no practical limit for how big the air resistance can be. Hear me out on this one. There is no practical limit for how big air resistance can be. Air resistance can be extremely big depending on how big of an object are you moving through air and how fast are you moving. Well, the other factor that is involved that I forgot to talk to you about it is that what is the area of this cross-sectional area of this cuboid object by which you are colliding with the air particles. If you have a bigger object, let's say if you have a much bigger object with a bigger surface to cross-sectional area, then you're definitely going to experience a bigger air resistance because you're simply going to collide with bigger number of particles. So practically three factors attribute towards air resistance. One is speed of the object. The two is cross-sectional area of the object. Cross-sectional area means the amount of area which actually collides with the air particles, cross-sectional area. And the third factor would be, I think it was it temperature? No. Was it density of air? No. Pressure? No. I forgot the third factor. আচ্ছা, থার্ড ফ্যাক্টর মনে পড়লে তোমাদেরকে বলবো না, সমস্যা নেই। এই দুটো ফ্যাক্টরই প্রাইমারিলি মেইন, আর হচ্ছে এই দুটো ফ্যাক্টর দিয়েই মোর অর লেস এয়ার রেজিস্ট্যান্স ডিপেন্ড হয়। What I was trying to go along is that air resistance practically don't have any upper limit. Whenever any object starts to move through air, the faster the object starts to start to go further, the more air resistance it will experience. And this is why every vehicle has, no matter how well made, no matter how aerodynamically good, no matter how nice or how powerful, no matter how many horsepower of engines it has, no matter how many cubic volumes of burn volume cc it has, it really doesn't matter. Okay. Every car or every vehicle has a top speed limit. What happens at the top speed limit? Now, this is the part that I really need you to understand because I'm trying to get to the idea of what we mean by terminal velocity. So this will be the term that we will require to understand. The idea of terminal velocity is that whenever any object is in a dynamic equilibrium case, dynamic equilibrium case means the object's velocity is not zero, which means the object is moving, but it has a resultant force zero condition, and it is very much possible. Let me give an example. Let's say we have a car over here. So let's say this is a car. We have the wheels, which is rubbing across the ground. And let's say the maximum amount of forward force the engine and the car and the wheel altogether can produce is, let's say, 1000 Newton. So the maximum forward force that between the friction of the track and the wheel this car can produce is in the forward direction of 1000 Newton. This is the maximum force the car can produce. So let's say the person puts in the keys, starts the car, presses on the accelerator all the way down. So the car is now producing 1000 Newton in the forward direction. So what happens? The car will start to speed up. Let's say at t equals to 0, the resultant force would be 1000 Newton because the car is still not moving. T equals to 0 means we just started to get the force. The car is about to move. This is the beginning of our observation. After 1 second, the car would have moved a certain distance and it would have a certain speed. Let's say the car is now moving at some speed in the forward direction, and we still have 1000 Newton forward force, but because now it is moving forward at some significant speed, we would have some air resistance coming working on the reverse direction. Let's say that air resistance currently is, let's say, maybe 200 Newton. Should I go 200? Okay, 200 is good. Actually, I should go 100. Let's say that backward speed is backward air resistance force is now 100 Newton. So at this instant of time, exactly at t equals to 1 second time, the resultant force that would be driving the car forward would now become 900 Newton. So the acceleration would fall, because currently at t equals to 0, this much equals to mass of the whole car, which is practically constant, multiplied by acceleration. This is the actual force. This is the actual acceleration. But whenever the car is moving forward, as the car speeds up, your backward force starts to increase. The more the car moves forward, let's say at t equals to 2 seconds, the car has a speed of something. We still have the same forward force of 1000 Newton, which we call the driving force, by the way, which is provided from the car's mechanism. And because the speed is much higher, let's say the backward force over here is about, let's say, maybe 300 Newton. So now the car would have a resultant force of only 700 Newton. And this is going to keep on happening. This is going to keep on happening till the point the car reaches a situation where the forward force of 1000 Newton provided by the car's engine and the friction of the road is perfectly balanced by the reverse force of air resistance of 1000 Newton. And this is the case where the car is not actually stopped. This car is slowly speeding up. And at this point, the car has some speed. And this is practically what I call the top speed of the car. The car cannot go any faster than this. Its engine and its equipments cannot develop any more force. So let's say, just for the sake of discussion, this car is equipped with some NOS, or nitrous gas, so which practically gives a huge speed boost. So let's say the NOS are pressed. Let's say the NOSes add another 500 Newton to the car's movement for the next 5 seconds maybe. So for the next 5 seconds, the car is going to start moving forward by the resultant force, which would be the 1500 minus the air resistance. I'm not writing a fixed value over here, because as the car will speed up, this 1000 Newton will start to go higher and higher and higher. So the backward force will simply become larger. But when the NOS runs out, once again, the car comes back to its original force of 1000 Newton, and simply the car will then actually slow down. It will not start to go backwards. Don't get the wrong idea. Let's say the NOS has run out after 5 seconds. So what is happening? Exactly after 5 seconds from here, let me draw a bit on the right. Exactly after 5 seconds over here, when the NOS has run out, but the car was accelerating under the effect of the NOS for that duration, the car now has 1000 Newton force in the forward direction because the NOS has run out. But the backward force, air resistance force, would be significantly bigger. Let's say that air resistance force is, let's say, 1250 Newton. I'm just coming up with these numbers randomly, keeping the concept even or in place. So at this instant, the car is moving forward. It has a forward velocity, but because the NOS is run out, the backward force is more, because earlier the force was provided from the car's engine plus the NOS effect. Now the NOS is run out, so only the engine fuel is providing the force. So now the car has a bigger backward force and a smaller forward force. So what is going to happen? Does the car start to move backward immediately? No. You now have a resultant force on the object which is working in the left direction, which has a value of, let's say, minus 250 Newton. So using this opposite force, the car is simply going to slow down. The car is going to slow down and eventually reach up to the same state of over here. It's going to come back to the same top speed of this scenario where the forward 1000 Newton was perfectly counterbalanced by the backward 1000 Newton of air resistance. And that's when the car will once again have the top speed value. And this is the whole idea of air resistance, that how the air resistance works. If we want to increase air resistance, we have to do a couple of things. First of all, if we want to increase the air resistance without actually moving the object faster, that helps significantly for the process of braking. We can use parachutes. There are a lot of drag racings racing, if you, for those who are into those things, you might have seen, they use long parachutes behind their back. I mean, once their quarter-mile track is finished, they actually deploy those parachutes and they can slowly slow down. That happens for a lot of tracks, and in cases where we have really well-engineered vehicles who actually compete for the land speed records, they also have very large parachutes. Whenever they are done close to the end of the track, they deploy the parachutes to increase their resistance by the increase of surface area so that they can break down faster. This is also equally applicable for a lot of supercars. For example, Bugatti Veyron and other supercars also adopted this process, that they have a flippable tail spoiler. Do you guys know what that is? I'm talking about this thing. This is the Bugatti Veyron, not this one. Yeah, this one. This is the Bugatti Veyron tail spoiler, which actually can rise up significantly higher, and it can actually tilt the angle of itself through some hydraulic mechanisms. This can give rise to significant high amount of force, which is gonna keep on. It is gonna produce some significant air resistance if we keep it in this manner, but this will also help to push the car onto the ground. This is like an. You have a look over here. The air molecules are coming over here, and they're getting up like that. So if the air particles are pushed up, the car will be pushed down. That's the whole way Newton's third law work. So whenever the and this spoiler is actually controlled automatically by the car's speed system, which is the brain of the car. It's I mean, the person doesn't actually have any control, manual control onto this tail. So as the car goes faster, this grip, this thing goes up, changes angle, and it goes into different variation of its positions and angles as well, making sure that the car is not losing grip from the track. So that's the purpose of this thing. And whenever someone is braking, this also comes into very handy. It actually goes all the way up and actually gets the biggest amount of angle so that people can brake really hard. And that actually is, this actually works as a air brake, and also works as a very good stability control mechanism, and so on and so forth. It's all done by the by having some control over the air resistance. Bugatti Veyron was not the first car to manipulate air resistance for their advantage, but they were the first group of people, I'd say, they could use it the most effective way, so that their car could go really high speed and still not losing control. And yeah, any questions so far about the whole air resistance shabang? Anything? Anyone? Am I muted?
No, sir.
So I understand that you kids got this idea. Maybe many of you actually knew this thing, but I just wanted to go through my process to give you an idea that terminal velocity is a thing, and objects can be in motion whenever their air is resultant force is 0. And this is what we're going to see for this scenario over here. Okay, to make sense of this graph, I'm going to need this white space. So I'm going to move this whole thing into something somewhere else. So where's my nope. Why am I so bad at this? Okay, so let air resistance be there, and Microsoft Whiteboard started to malfunction a little bit, taking time to respond. Please respond. Nothing is happening. Oops. আচ্ছা, মেবি ওই পুরাটুকুতে অনেক ডেটা আছে সেজন্য মনে ঝামেলা হইতেছে। I'm just gonna move the graph down because basically the same thing working around. কি সমস্যা? Beautiful. So what happens for each of these individual segments? So let's go one by one. Now, one of the things that I really want you to understand is that you kids have to properly conceive the idea of what we mean by negligible. I talked about this a bit earlier. Just a quick brush up. Negligible is something that we consider to be very small compared to the other things involved. Negligible is something that is considered to be too small compared to the other similar things involved. One of the things that we have to understand that in this example that this person is parachutist is about to fall down, throughout his entire motion, the downward force, one downward force would be always constant, and that downward force is called weight. Weight will be a constant force. What will change is the air resistance. Air resistance will change in value, air resistance will change in direction. Air resistance is gonna cause us the variation of this holograph. Now, like I said, the air resistance is highly dependent on the speed of the object. If we have an object moving at a very low speed, the air resistance can be considered to be negligible. So because of that, this Parachutist graph for a small starting segment of OA has an apparent straight line graph, proving that the person is only having an uniform acceleration, and the gradient of this graph of this segment, OA segmented gradient hobe hocche, I'm using the term m as gradient, or actually can write actually a, acceleration is equal to 10 meter per second square. And we, for this scenario, we're considering air resistance to be absolutely negligible. But if you ask me, is it truly negligible? The answer is mathematically no. Object moving through air, you're colliding with air particles, so you have air resistance. But the value of that air resistance, upward air resistance, would be too small because the weight would be too big for the first couple of seconds of the fall. So that's what we represent over here. If some graph actually shows up that starts to curve from the very first point, you should not consider that graph to be wrong. That is a graph for a parachutist where the air resistance was considered to be a significant force from the very beginning. Do you get my point? For the first couple of seconds, when the person is falling at a pretty low speed, we are considering the air resistance to be significantly small. That's it. So that's the OA segment. So this is here the person is falling. Our GP is decreasing and kinetic energy is increasing, and the speed of the object increasing uniformly or constant acceleration. OA segment is very simple. What is happening at AB? Within the AB segment, person is still falling, but we have a decreasing gradient graph, which means the downward acceleration is now decreasing and eventually reaches to 0. At B point, the graph is starting to become horizontal, representing that from the point B, the downward acceleration became 0, which means the person now achieved a state of dynamic equilibrium. If the person is falling through air at a pretty high speed, this is the value of that speed, which we call terminal velocity, but the person has achieved equilibrium of forces, which means currently his weight downwards and air resistance upwards, they have both matched each other. So the person is under the effect of no resultant force. He's still falling downwards because we know inertia, the idea of Newton's first law tells us what, that if any object is not under the effect of any force, it will keep maintaining its velocity. So whenever we reach the condition state of equilibrium of forces, the object would maintain its velocity. So here we get the equilibrium force situation when the object is falling, so the object will keep falling. So for the segment AB, we have decreasing acceleration, of fall, আচ্ছা, এখানে আমি একটা জিনিস বললাম তোমাদেরকে, আমি খুব ক্লিয়ারলি বলি, এই জিনিসটা খুব ভালো করে খেয়াল করো। Decreasing acceleration is not deceleration. Think about it. I'll say it again. Decreasing acceleration is not deceleration. Are you getting my point? I'll write this over here. This is very important not to mess up. Hear me out. Decreasing acceleration means the object is accelerating. It's speeding up, but it is not speeding up as much as time goes on. Its value of acceleration, its rate of speeding up is becoming less. Whereas deceleration means the object is slowing down. They are not the same thing. Decreasing acceleration means object is speeding up at a slower rate than earlier. Deceleration means object is slowing down. They are not the same thing. Don't get the wrong concept. As long as you see the velocity is increasing, it's still acceleration, but the magnitude of that acceleration is slowly becoming less. So object is accelerating less and less and less. Is the speed of the object increasing? Yes. Is it increasing as fast as before? No, it is increasing at a less rate than before. That's the difference. So this is the decreasing acceleration scenario. And at the final situation at B point, the acceleration becomes zero. So decreasing acceleration to 0. And then for this segment, once again, you have to understand this part. As the object starts to experience significant air resistance, মানে আচ্ছা, এখানে আমি আরেকটা জিনিস লিখি নাই, সেটা হচ্ছে I should have written the equation delta GPE equals to delta KE. বলো না, এই জিনিসটা খেয়াল করো, আমি অ্যাকচুয়ালি ইকুয়েশন ফর্মে লিখলে ভালো হতো। ডেল্টা মিন্স চেঞ্জ, ডেল্টা জিপি ইকুয়ালস টু ডেল্টা কে, মানে হচ্ছে এবি সেগমেন্টের জন্য যতটুকু জিপি লস হয়েছে ততটুকু জিপি কাইনেটিক এনার্জিতে কনভার্ট হয়েছে। অল দ্য জিপি লস্ট হ্যাজ বিন কনভার্টেড টু কাইনেটিক এনার্জি, so there is no air resistance related loss. For the AB segment we have significant air resistance, so how the equation is going to look like, so we have delta GP which should be converted to some gain of kinetic energy, and we should have some significant air resistance loss. So I'm going to write this as AL, air resistance loss. So GP of the object is being lost, so GP is going down, K is increasing, and air resistance related loss is also increasing. And so now you might wonder that what actually happens to this amount of energy. The object is losing some amount of GP, a portion of that GP is converting to air resistance loss. So what happens to that energy? In macro example, this energy is absorbed in the atmosphere as heat energy. Now you might wonder, what heat energy? I mean, the person is falling down, where does the heat energy comes from? Now here's a bit of an idea. Try to bear with me. How do we express the form of energy that is heat? Heat energy of an object is basically the type of energy that an object has stored within itself by virtue of its particles motion, not its whole motion. If an object is altogether moving, that's kinetic energy. If the object's particles within itself has some sort of motion, that may be vibration, that can be actual translation moving from point A to point B, or it can be a combination of both. If an object has some stored energy within itself by virtue of its particles motion, that type of energy is essentially what we express as heat energy. As long as the object has some heat energy, you could possibly extract that out. The moment the object loses all of its particles motion is when the object has no heat energy, which is only possible to achieve at absolute zero temperature, which is 0 Kelvin. We're going to talk about these stuffs in more detail in the temperature chapter. But I'm trying to give you the idea for heat energy because I want you to understand that heat energy is the amount of energy, is the type of energy that is expressed by virtue of the particles movement of an object. Now try to understand, air particles, before the person actually goes through the atmosphere, a certain part of the atmosphere, air particles were doing their own motion. They are moving Brownian motion left and right. They are colliding with each other and whatnot. When the person falls through them, doesn't that person add a bit more motion to all of those air particles that he passed through, because he actually disturbs their original movement? That additional amount of energy is actually heats up the air molecules of that vertical fall through which the person is falling through, and that is something that we express that this will convert it into heat energy of the atmosphere. Now you might wonder that doesn't make sense. I mean, where is the heat? I mean, would the person feel hot? Well, the person might feel hot if they actually fell through that much air resistance, or if they were falling through that much at that much speed, which should give them that air resistance. Actually, objects falling through atmosphere does experience a significant amount of heat whenever we talk about re-entry. Re-entry means if we have a rocket or a spaceship that is about to enter back into Earth's atmosphere, which is very common for whenever astronauts are coming back to Earth, they actually have to go through the entire thickness of the air of the atmosphere, and in their falling in their fall, at some point they experience some significantly high amount of heat generation with their capsule. That's pretty much not the case for a simple parachutist, because they don't actually fall to the entire length of the atmosphere, and also they don't ever fall through with that much high speed that they would actually produce that much sensible heat energy within their body. But if you wonder, do they heat up? Yes. Can they perceive it? In most cases, no. Do you understand the concept of the heat energy conversion?
Sir, could you go over once again?
In simpler words, that as the person falls through the atmosphere, he collides with the atmospheric particles, so he moves the air particles more than they would have moved if he was not falling through. That additional amount of movement is expressed as the heat energy gain of the atmosphere through which the person is falling through. This amount of energy is distributed over a huge amount this amount of energy is distributed over a large number of air particles, so the effect of temperature rise is almost imperceptible. Make sense?
Yes, sir.
আচ্ছা, কার কোনো কোশ্চেন থাকলে প্লিজ বলো, or if you want me to yes
স্যার, এই হিট এনার্জি যেগুলি প্রডিউস হয় এটার জন্য কি স্যার মিটিওরস যেগুলি আর্থের দিকে পড়ে ওইগুলি বার্ন আউট হয়ে যায়?
কি পরের পার্টটা কি বলছো
স্যার? যখন হলো মিটিওরস পড়ে আর্থে, এই হিট এনার্জির জন্য কি ওইগুলি বার্ন হয়ে যায়? কয়েকটা তো গ্রাউন্ড হিট করার আগেই বার্ন আউট হয়ে যায়।
মানে স্পেসশিপের যে কভারটা থাকে সেটা?
না স্যার, লাইক স্পেস থেকে যে মিটিওরস পড়ে না।
আচ্ছা আচ্ছা, হ্যাঁ হ্যাঁ হ্যাঁ, precisely, yes, sorry, I was not hearing your question right, my bad. Yes, precisely, yes, this is exactly why most of the meteors don't reach to our surface, because they burn out in the atmosphere. Yes
Sir, are these heat particles responsible for that? Sir, এই হিট পার্টিকেল গুলির জন্য কি হয়? হ্যালো,
I'm not sure why, but আমি তোমার কথা অনেক echo দিয়ে শুনতেছি।
sir, I will type it out.
আচ্ছা, তুমি আমাকে পারলে লিখে দাও, আমি তারপর তোমার কোশ্চেন আনসার দিচ্ছি। I'm really sorry, I cannot hear you right. আচ্ছা, এটা গেল একটা পার্ট। নেক্সট যে জিনিসটা হবে সেটা হচ্ছে, আচ্ছা এখানে আমাদের কাইনেটিক এনার্জি গেইন হচ্ছে এবং অ্যাটমসফিয়ারিক লসটা হচ্ছে এবং অ্যাক্সিলারেশন ডিক্রিজেস টু 0। আচ্ছা, what happens for the BC segment? Try to understand over here. BC is the segment where the person is reaching the first terminal velocity, which means the parachutes are still closed in his backpack. Okay, Taisir gave us the question that, sir, are these heat particles the reason why the meteors burn out before they reach out the surface? Yes, precisely. This is the reason, and there are still some meteors which can be found on Earth's surface. These are considered to be pretty large meteorite, which had enough mass that even after they burn through the atmosphere and whenever they reach the Earth's surface, they still had some mass available. And if they have some significant amount of mass, they might actually make a huge amount of blast, which one of which actually happened is thought to is the reason for the extinction of the dinosaurs and such. But most meteorites are actually small, and we don't even know about this because we are not affected by those. Yeah. Okay, for the BC segment, the person falls at a constant downward speed, which you call the terminal velocity. And within this part, the person maintains a constant velocity, so there is no K gain. So he only loses GP because he's still falling down, and all of his lost GP will be converted to air resistance loss completely. So what happens over here? Constant velocity. We could also write this as terminal velocity. Terminal velocity. And here we have some energy losses. So delta GP is absolutely equals to air resistance loss. So GP is lost, air resistance is gaining those GP lost amount of energy. Now, what happens at point C? This is a part that we really need to understand. At point C, the person opens the parachute. So what is going to happen when the person opens the parachute? This is what's going to happen. Through his fall, his entire body, so head, two hands, hoping he has all the limbs, so I'm using a standard person. So head, two hands, the torso, and the two legs. The person was causing some air resistance with this much surface area with the atmosphere. The moment the person opens the parachute, he suddenly increases the contact area with atmosphere. I'm using a specific word here. He suddenly increases the contact area with atmosphere. Now he's colliding with the air particles with his body, because he didn't become a ball. He's still spread out. He's making the collision with his body. Additional to that, he has a large amount of surface area of the canopy of the parachute, with which he's also colliding with that air particles. So now, because of the sudden increase in air resistance, sudden increase of surface area, the air resistance will suddenly become very, very small, very strong. Air resistance will suddenly become very, very strong. আচ্ছা, এখানে আমি আরেকটা জিনিস লিখতে ভুলে গেছি উপরের পার্টগুলো থেকে, সেটা হচ্ছে within this part, resultant force is weight working downwards. Within this part, resultant force is equals to weight minus air resistance working down. For the BC part, resultant force equals to 0 because weight equals to air resistance. For the CD part, CD segment, the moment the air parachute is opened, suddenly we have a very large rise of air resistance. So try to understand this thing. The person is falling down. He has a weight which is working downwards. Right before C, we had equilibrium of forces. So we had downward force equals to upward force. The moment the parachute is on, now you might wonder, so parachute ki immediately on hoise? Well, my graph is not actually drawn to scale. If we plot this whole journey in terms of minute, we can actually give a sharp corner. But if you want to plot this in terms of second, particularly that is zooming on onto the graph, actually this part of the graph might actually look like a bit of a curve like that. Because it takes some time for the parachute to come out of the backpack and actually unfold itself so that it can actually capture enough amount of air. It actually takes some time, couple of seconds maybe. So within that second, we're gonna have a bit of a curve. But for your syllabus volume, for most purposes, I mean, I'd say let's say 99% of the graphs, I have seen that this is a corner, sharp corner. So you might actually draw a sharp corner, which is perfectly acceptable. I still covered the part that why it can be a curve. If we just zoom on the graph, it takes some time. So depending upon what scale of time are you using on the time axis, are you using minutes, or are you using seconds, or are you using milliseconds or microseconds, depending upon that, your this corner can have different shapes. Irrespective, whenever the parachute is open, suddenly we have a large surface area, that suddenly the air resistance is going to increase, and this increase of air resistance will be a sudden increase. This is a very important part. This will not be a gradual increase of air resistance of like what happened over this segment. This would be a sudden increase of air resistance, which would be more than the weight. So within this segment, I'm going to write parachute is opened. sudden increase in air resistance. So now resultant force equals to air resistance minus W working upwards. Here is the bigger force. Person decelerates decreasingly, which means now the person is going to start to slow down, and eventually the slowing down will also slow down to not slowing down anymore. So the person will once again reach a constant terminal velocity at D point. I would like to talk a little bit about what happens over here. Many of us have the idea that whenever the parachute is open, the person starts to go up. This is a wrong idea. The reason we have this idea is that we have seen the parachute jumping in all of us, our experiences in some sort of video. Like there is a person, maybe Tom Cruise is taking some impossible jumps, and there is a cameraman. So the way these shots are taken is this: that both the cameraman and the what can I say, actor Tom Cruise, or both the parachutist and the cameraman, they're both falling, and the camera is aiming at the parachutist. He's doing his job, fighting or doing weird stuff or whatever action stuff. And when they are done with their job, they open the parachute. Cameraman didn't yet open their parachute, because the person who is being videoed opens the parachute earlier. For the frame of the camera, we see that the person starts to go up. You have to understand, the person doesn't start to go up. He just starts falling at a lower rate. The person who is holding the camera keeps on falling at the same rate. They open the parachute later. That's why the person is always seen to go up. So if you hold both of your hands a bit high above your head and start to pull them down slowly, when the person opens the parachute, they start to fall slower, and the person who didn't open the parachute still keeps falling fast. And that's why within the frame of the video, it appears that the person starts to go up. The person actually in true case never goes up. They will always fall down. Mark my words. Here I wrote this. Throughout this entire parachutist graph, the person is always falling down. They're never going up. So opening the parachute does not make them go up. You might wonder, well, we have an upward force. Why wouldn't the person go up? Good. The person was falling downwards at a very high speed. We do have an upward force. Beautiful. But if you want to make an object go upwards while it was moving, falling downwards at a very high speed, first you have to decelerate the object to zero. Only then you can start to push the object upwards. Without making it come to rest in a downward motion, you cannot make it go up. The person was not brought down to rest. You can see the whole graph in this graph, this entire graph is existing on the same side of the x-axis, which means this whole part represents the same direction of motion. Do you understand this idea? This is kind of a bit a small paradox that we have, because we have seen so many of these videos, but that's not what actually happens in real world. No one starts to go up when the parachute is open. Just whoever has opened their parachute starts to fall slowly. That's it. বুঝা গেছে? Okay. So this is what is happening. Person decelerates decreasingly. So when the person is decelerating decreasingly, essentially একটু পরে কি হবে? Eventually they reaches the second terminal velocity at the point of which I'm going to write in D section. What happens for this segment over here for the energy change? We're going to have delta GP plus delta K. Now I'm going to explain this part. Equals to air resistance. Now you might wonder, air resistance loss. So I'm going to write AL. So what is happening? The person is still falling. He's still falling. So he's losing GP, and the person is slowing down. Get that in your head. He is falling down and slowing down, which means he's losing GP because of the fall. And because he's slowing down, he's also losing K. So both of this energy will be given to the atmospheric particles who are responsible for this. So In this case, the person, our K will drop, GP is definitely dropping throughout the whole process. GP is dropping because the person is falling, but now K will also drop, and both of their total sum would be converted to the atmospheric loss, atmospheric air resistance loss. So that's the scenario that's going to happen for CD part. What happens for the D part? We have the second terminal velocity. So we have resultant force 0, because now resultant force is once again, this is happening because now weight has once again becomes air resistance, and the person has a second terminal velocity, much smaller because now we have a bigger surface area, and the person keeps on falling with this part. And E is basically the point where the person lands on the ground. So at E, person or air parachutist lands. So landing এর পার্টটা আমি এখানে একটা ভার্টিক্যাল লাইন হিসেবে দেখাইছি, বাট অ্যাকচুয়ালি এটা কখনোই অ্যাকচুয়ালি ভিটি গ্রাফে কোনো পার্টই প্র্যাকটিক্যালি ভার্টিক্যাল হওয়া পসিবল না। এইটা বুঝো, ফিজিক্যাল অবজেক্টের জন্য ভিটি গ্রাফে কোনো পার্ট প্র্যাকটিক্যালি ভার্টিক্যাল হওয়া পসিবল না, কারণ ভিটি গ্রাফে কোনো একটা পার্ট, any part of the VT graph being vertical means what? For that segment, for that small segment, no matter how small that is, the acceleration of the object is infinite. You cannot have infinite acceleration. Objects will always have some measurable mass. If you want an F equals to ma, if you want to get an infinite acceleration, you need to provide an infinite force. You simply cannot get infinite acceleration. So any part of a VT graph should not be perfectly vertical. It might appear vertical, which means it is appearing vertical, which means it's a large acceleration. But if you really zoom in on the graph, it will definitely start to show you some sort of curve. No part of a VT graph for a realistic object, for a realistic scenario, should be vertical, because that is not possible. Although it appears to be vertical over here, because what I'm trying to show you over here is that for this entire journey period, when the person actually hits the ground, I mean, try to visualize a person is falling with their parachute open towards the ground. Now how they're going to come to stop? Their legs are going to touch the ground, and then their body is going to fall on the ground, and they're going to come to rest. That is the amount of duration compared to the whole time that we have over here. So that amount of deceleration will happen within a very short amount of time. That's why I have drawn this apparent vertical line. But to be honest, this should in a really zoomed in scenario, this part should look somewhat like this. There should be some time amount, and the person should have some negative acceleration, eventually making the person to reach to rest. So for a practical graph, we can have all of this, but I mean, this segment of the graph, I mean, this the starting part of the CD graph, I mean, this segment of the graph can also appear to be a vertical line in some cases. But one thing is really important: no part of this graph should be going backwards. I mean, sometimes the students are asked to draw a parachutist graph, and many students draw graphs like this. Don't do that. Drawing a graph like this means whenever the person opens the parachute, they go back into time. Like they were at this time frame, the moment they open the parachute, they start to go back in time. A parachute is not a time machine. I mean, they cannot go back into time with a parachute. So the graph will always be from left to right, continuous graph, and logically it shouldn't be vertical. By no means it should be going backwards. That's not supposed to happen. Any questions so far? Anyone? AB, yeah, sure. I can explain AB again. No big deal. Let's have a look over here. The segment AB says that it is a decreasing acceleration to 0. Decreasing acceleration to 0. It means at A you have the biggest amount of acceleration, which is downward acceleration of 10 meters per second square, which is the end point of OA segment. From A, we are considering the resistance to start to have a significant effect, which is causing the object's acceleration to slowly reduce. The object is still speeding up downwards, but it is not speeding up as much. If I give you some numerical example, might as well be easier for you to grasp. let's say within this segment, every second the increase of downward speed was 10 meter per second. Every second the speed downward was increasing at 10 meter per second, 10 meter per second, 10 meter per second, 10 meter per second. But for this segment, as the object falls down, your downward speed increase will happen, but that amount of increase will reduce. For example, let's say right at A, you have an increase of 10 meter per second. Let's say after 1 second, within the second duration, second, your increase is going to be, let's say, maybe 9.5 second. Within the next second, you might have 9 seconds. Within the next second, you might have 8 seconds. Within the next amount of time, you might have 6.5 seconds. I'm not going to the mathematical jibber jabber, but what I'm trying to elaborate to you that the gain of speed will become at a lower rate. That's what we mean by decreasing acceleration. Ultimately, at B point, that acceleration, downward acceleration value will become 0, which means now the forces would have balanced up. So the resultant force would be 0, but at that point, the object will start moving downwards at a constant speed, pretty much like what happens for the land speed, top speed for fast cars. Make sense? Okay, good. Okay, I'll take a small break. I'll keep this part in your view. I'll mute the channel, pause the recording. I'll be back in, let's say, 5 minutes. So we started the recording. We're gonna see some question regarding these kind of scenarios, what we have and what we might have to do from worksheets. Okay. This is the whole P1 compilation. We'll jump into chapter 2. So আচ্ছা, তোমরা কি ওয়ার্কশিট কালেক্ট করছো কেউ?
worksheet.
আচ্ছা, ঠিক আছে, তোমাদেরকে এগুলা মেইল করে পাঠানোর ব্যবস্থা করতেছি, পাঠাও দিয়ে, প্যারা নাই। Let's have a look at this question. You can use your ruler on the screen to judge the correct response for this question. I'm going for 21. See if you can get a correct answer for this. Have a look. Which one do you think is the correct response? ওহো, তোমাদেরকে তো আমি ভেক্টর ডায়াগ্রামের রুল পড়াই নাই, পড়াইছি? ট্রায়াঙ্গেল রুল, প্যারালোগ্রাম রুল পড়াইছি এগুলা?
No, sir.
ওকে, দ্যাট ইজ লেফট। আচ্ছা, ঠিক আছে, এটা তাহলে এখানে থাক, তোমাদেরকে ভেক্টর ডায়াগ্রাম পড়াই। So let's pick up the next topic that we have in sequence, which are the vector diagrams. So vector diagrams are practically of 3 types. For our syllabus, we're gonna only look at 2 types. We're not gonna look at the polygon rule. The first one is the triangle rule. The second one is parallelogram rule. And the third one is polygon rule. আমাদের এই দুটো ও লেভেলসে আছে। আমাদের এই দুইটা ও লেভেলসে আছে, এটা আমরা এসে গিয়ে দেখবো, সো এটা আপাতত বাদ। I'm going to write some terms over here. To understand these two rules, let's just get a couple of things first. First of all, whenever for both of these rules, triangle rule and parallelogram rule, we're going to see the finding process of the resultant vector for two vector quantities. So how it's going to look like? It's very simple. Let's say resultant vector r is given by two vector quantities, let's say x plus y. So I'm going to give vector sense on them. So the single vector that we want to find out, that's what we call the resultant. The two vectors which should be added to get this resultant vector, these are the vectors that we call component vectors. So x is a component vector of r, y is a component vector of r. The sum of these two gives us the resultant vector. In the same process, we can also do subtraction of vectors. Subtraction of vectors একটু পরে দেখাচ্ছি। Vector diagram আকার, one of the first step towards drawing a vector diagram is that we have to draw the vectors in scale and in correct direction with respect to each other. What does it mean? It means maybe something like this. So we have an object over here, and the question says that this object is subject to two forces. One goes in this direction. Let's say that is 60 Newton. Let's say this is the horizontal line. With the horizontal line, this one has an angle of, let's say, maybe 35 degrees. And let's say another force is working in this direction. Let's say this is 40 Newton, producing an angle of maybe 70 degrees. So we have this thing given, and the question is asking us that we have to draw the resultant of these two forces. The arrow lengths of the question can be in different size, because typically in the question the figures are not given to scale, but for a vector diagram you have to draw them in scale. Drawing in scale means you have to choose a certain ratio of conversion. You have to choose a certain ratio of conversion that is convenient for you to draw, and that does not essentially make the figure too small. The figure should be acceptably large, yet it should be accommodating within the amount of space that the question has given you. Depending upon these two factors, you should choose a conversion scale. For example, if we choose for this figure, maybe let's say 10 Newton for 1 centimeter, that would mean a 60 Newton force would be represented by 6 centimeter, and a 40 Newton force would be represented by 4 centimeter. That's one scale. So a scale, this is what we call the scale. I have written these numbers over here to give you the idea for what the scale actually is gonna do for us. Which means if we choose this scale, in our diagram, the 60 Newton force should be represented by an arrow length, which should have a length of 6 centimeter, and the 40 Newton force should have an arrow length which has a length of 4 centimeter. That's the idea of scale. If you want your figure to be slightly bigger, you can choose a different value. Maybe if we want to go for this ratio, let's say 10 centimeter for 10 Newton for 2 centimeter. Now this is actually not defined as a scale. If we want to define a certain expression as a scale, one of the quantities has to be 1. So if I just divide both sides by 2, I can write 5 Newton for 1 centimeter. If we choose this one as our scale, we can also once again get this number. So that would mean 60 Newton force should be represented by an arrow length of 12 centimeter, and 40 Newton force should be represented by an arrow length of 8 centimeter. Now the question is that you should judge within the amount of space that you have available within your copy, that which figure is possible for you to draw. If we want, we can draw these forces in a tilted direction, not in the exact direction that the question gives us, and we can perfectly draw it, no big deal. But my recommendation is that preferably don't do that. I'll tell you what both of these things mean. one of the ways that we can go for drawing these two forces. So first, I'm going to show you how to draw the parallelogram rule because that's easier to grasp in most cases. And then I'm going to show you the triangle rule. For your exam, if the question doesn't specify that which rule do they want you to draw, if they just say draw a vector diagram, you can draw either of those. You can choose to draw a parallelogram rule, you can choose to draw a triangle rule. It's up to your wish. But if the question specifies, sometimes they do that use a triangle rule to find out the resultant, then you have to draw it in triangle rule. If you in those questions do a parallelogram rule, then if your whole procedure is correct, your answer is correct, you're gonna lose 1 mark for not reading the question. So we are gonna learn both of them because sometimes the question stipulates exactly which method should you draw your vector diagram by. So if we go for a parallelogram rule, I mean the way that I recommend, I personally feel comfortable and the students also find it easier to do, is that do not mess up the arrow directions of these forces. So with the horizontal, this force was drawn at 35 degrees. So you just draw a horizontal line with dotted line. Choose one point as your starting point. Put up your protractor, give a dot at the 35-degree mark, and on the other side, give a dot at the 70-degree mark from your protractor. So 30-degree mark should be a bit lower. Maybe somewhat over here. Actually, এখানে প্রোটেক্টর ইউজ করার সিস্টেম আছে, বাট এটা আমি প্রোটেক্টর কেমন ইউজ করতে হয় এটা আমি পুরোপুরি পাই না। সো I don't know how to use this ruler properly. So yeah, I'm just gonna assume these positions. Okay, how do I get rid of this thing? Ruler gone. So let's say we have given these two dots. Now you're gonna hold your ruler with the starting point and with the given dot, and for this direction you are trying to draw a 60 Newton. So if I go for this ratio, use your ruler to draw a perfectly 6 centimeter length of line. Let's say that line finishes over here. You can give the arrow at the tip, you can give the arrow at the middle, doesn't matter, but you have to give the arrow. And then the other force, let's say 40 Newton, that should be over here. So you draw this up over here. That's a straight line. A bit less should be good. Maybe this much easier, 4 centimeters. So this arrowhead has a 6 centimeter length. This has a perfectly 4 centimeter length, and you have to draw up those angles that is required. Okay. I just saw the chat window. One of your classmates asked me a question: is that why do parachutes have holes? If we want to increase the air resistance, wouldn't we want to create the parachute without any holes to increase the area of contact? Okay. The reason we want holes in a parachute, I mean, so that whenever the parachute is falling down, air has a directed way to flow through the parachute and leave out to the top. That's for the early parachutes which were used in World War II. I mean, they were just deploying all the paratroopers, and they would have no way to control where they would land. They would just fall wherever wind takes them. They had one small hole at the tip of their parachute so that the air would not actually fold it all together, because if you have the whole parachute without any hole, in that case the air is gonna get capped, and if you have some really stormy weather or such, the parachute can actually fold within itself. But if you have a straightaway path for the air to pass through, you are creating significant air resistance, yet you are making sure the parachute remains open. That's what happened for the World War II parachutes. But later what was found out that if we make some horizontal holes to the parachute, we can get some significant air resistance to give the parachutist safe landing speed. At the same time, we can also allow the parachutists to glide their parachute in a specific direction by pulling strings on the two sides of the parachute. I mean, you can actually close down the holes on one side and have bigger holes on the other side to make your parachute turn. So that gives a significant maneuverability for the parachutist. So that's what the holes actually do. They actually helps for a better control while falling through. Make sense? Okay. Coming back to the angle thing. So you have to label this angle over here. You should also label this angle over here. And then you should label these two arrowheads. So now I'm doing the parallelogram rule because I have a look over here. In the parallelogram rule, I wrote that component vectors are drawn from the same point. This is the key phrase. This is the key phrase for the parallelogram rule, where the triangle rule's key phrase is this: component vectors are drawn one after another. This is the key difference point you should have in your head. So here I have drawn these two vectors over here, and I should label them as 60 Newton, not 6 centimeter. Whatever the vector quantity the question has given me. If I have drawn over here as forces, these two vector quantities could be velocities, these two vector quantities, both of them could be displacement. So you look up in your question and you write that unit. And now you have to complete the parallelogram. Now completing the parallelogram is usually done by drawing parallel lines on both sides. You can use your pencil compass to do that. For those of you who know how to do this, well and good. For those of you who have forgotten how to do it, because I'm pretty sure you are practiced to do this, it's very simple. You take up your pencil compass, put the pin over here and the pencil over here, and take this much arc for in your pencil compass. Then put the pin over here and draw an arc. Draw an arc which has the length of 6 centimeter. Repeat the same process for the 40 Newton side. While so you put your pin over here and your pencil over here, take this much length, then sorry, then put the process over, repeat the process over here, and that should give you two equal length sides, and simply join the cross point of these two arcs. That gives you a parallelogram. You don't have to rub off the arcs. You don't have to. You can just keep it over there. Examiners are not going to be bothered by that. That's your parallelogram. And then you have to join the center line from the same starting point. You have to draw the diagonal. Drawing of the diagonal usually represented by double arrow, but you can choose to give one arrow, doesn't matter. This is your resultant. We usually label this as R. If you have some other letters to represent it by, you can also label that. You don't have to write numbers over here. But in your equation, there would be space that what is the resultant. Now, whenever they're asking you to find out vector quantity, they're essentially asking for value, which is magnitude, and they're also asking for direction. So you have to give both of them. Now, how can we give the value? Value is very simple. The scale over here we use is 1 centimeter for 10 Newton. So you're going to measure the length of this diagonal with your ruler, and then simply multiply that centimeter length into 10 with 10, and that gives your resultant length. Let's say that value would be maybe, I don't know how much, 72.5. I'm just coming up with random numbers. I don't know how much that is. I'm just assuming this number. And then you have to write the direction. Now the direction can be written in a lot of different ways. For this question, I mean, the most common way we can write the direction is with respect to any of the component vectors. We can try to write what is the angle between resultant and x vector. You can write that, or we can also write what is the angle between resultant and the y vector. Any of these two choices are okay. Sometimes we deviate from these choices. That depends upon the ease of expression. Because let me just tell you, using a protractor, you can measure this angle. Now be careful when you're measuring this angle, because if you're trying to measure this angle, you should put your protractor like this. And that is your angle between these two sides, not on the horizontal line. Your 0, 0 line should be aligned with one of the reference line, and the other line should give you the measurement of angle. So if you put it this way, you get, let's say, you get this angle. Let's say this angle is maybe, let's say it is, this angle is theta. I'm not sure. So I'm going to write theta degrees. Or you could find it out from here as well. Let's say this angle is alpha. So you could write, so if you write theta degree, you should write theta degree with 60 Newton. That's the expression that you are now choosing to write the resultant angle with the 60 Newton force. Or you could write alpha, you could measure this angle, or you could write this one, or I'm using double slash, or you could write alpha degree with 40 Newton. That is also perfectly acceptable. Either of these expression is good. What the deviation can be, we can also choose to express the angle with the horizontal. Because in the figure both the 35° and the 70° were given with respect to the horizontal. There is a dotted line over here representing the horizontal line. So if you want, you can also measure this angle. Let's say this angle is beta. You measure this angle. So to measure that angle, you have to put your protector in this fashion. So put your protector like that, measure up the whole angle that you have from here to here. And you can also write, let's say, beta degree with horizontal. That will be also perfectly acceptable. This is how we actually measure the angle and come up with the answer. এটুকু হচ্ছে প্যারালোগ্রাম রুলের হাবিজাবি। বুঝা গেছে কিনা? Any question? আচ্ছা, apparently no. The second thing that we have is the triangle rule. Triangle rule basic idea হচ্ছে component vectors are drawn one after another. আচ্ছা, to draw this same exact figure in triangle rule, I'm going to keep this figure on the upper right corner, and then I'm going to try to draw the triangle rule over here. For triangle rule, the vectors should be placed one after another. So the point where one vector finishes is exactly from that point the second vector should start. একটা ভেক্টর যেখানে শেষ হবে আরেকটা ভেক্টর ওখান থেকে শুরু হবে. You can either draw this in 60 Newton 40 Newton pattern, acceptable, or you could draw this in 40 Newton 60 Newton pattern, also acceptable. The sequence doesn't matter. The sequence simply doesn't matter. You can draw any of them first, but একটা যেখানে শেষ হবে তোমাকে সেকেন্ড ভেক্টরটা ওই পয়েন্ট থেকে স্টার্ট করতে। They should be drawn one after another. So you draw one, and at the end point of the first one, you start the second one, and you keep on drawing. And obviously you have to maintain the scale. So এই গ্রাফটা আমরা কিভাবে এই ডায়াগ্রামটা আমরা কিভাবে ইজিলি আঁকতে পারি? First of all, we are gonna draw a horizontal line. Let's say if I want to draw the 60 Newton first, I'm gonna choose one point over here. Use my protector. I'm gonna label this 35° angle. Draw a 6 centimeter line. And label these three things: 35 degrees, arrow, 60 Newton. And then at this point, I have to draw the 40 Newton force. Now have a look. The 40 Newton force was shown to have the 70° angle with the horizontal. So to be able to draw this angle, I have to draw another horizontal line right over here. That is the additional drawing that you have to do. So just hold up your ruler and you draw a perfect parallel line with the bottom line, which should be a horizontal line right over here. You don't need it that big. I'm just showing it long to give you the idea that these two lines are to be parallel to each other. And from this line, you draw a 70° angle. And you draw a 44 centimeter line, which should be labeled as 40 Newton, labeled 70° right over here. And then you simply join from the first to the end. So I'm going to show you one part of the writing. Have a look in the description of the triangle rule. Component vectors are drawn one after another. Third set gives resultant in opposite order / sequence. Third side gives resultant in opposite order / sequence. Now, what does it mean? It means, have a look. In cyclic order, this arrow is going this way. This arrow was going this way. So if you want to complete the triangle in one stroke of pencil, this would be the regular way of the completing side. This would be the cyclic order of forces. However, in the triangle rule, this third side would give you the resultant in the opposite order of the other two. What it means is that the resultant should not be in the same sequence as the other two forces, rather it would be in the opposite sequence. An easier way to remember this thing is that the resultant will be drawn from the start point of the first vector to the end point of the last vector. That is also an easier version or easier way to remember this thing. So you're going to complete this triangle rule, and this is your resultant vector. You can label this as R, and you don't have to label anything else on the figure. Then we just measure this length, and in the same way that you have mentioned earlier, you can go ahead and write these angles that what over here, that whatever the angle that you get. So if you're trying to represent it for between 60 and r, maybe this is the angle theta. If you're trying to represent it between 40 and r, maybe this is the angle that you're gonna go for. Or if you want to measure this whole angle, you can also choose this angle, no big deal. বুঝে গেছে? এখন I hope it makes sense. And most common mistake টা কি হয়, স্টুডেন্টরা যখন ভেক্টর ডায়াগ্রাম আঁকে, whenever they're trying to draw a vector diagram in the exam, what is the most common mistake? This is the most common mistake that happens, and you should not do that, which is a mix up of these two rules. Let's say this is the same question that we're trying to solve. What the students in many cases do, they start pretty well. They draw the 60 Newton, they draw the 40 Newton. Actually, I messed up the alignments. They draw the 60 Newton, and then they draw the 40 Newton. And they do all the labelings as well. Good and good. 45 degree, 70 degree, well and good. And then they forget that they were attempting it in the parallelogram rule. They see two sides, and they just simply join these two lines. And out of some imagination, definitely out of imagination, they choose any direction to give. Sometimes they give this way, sometimes they give this way, whatever their mind tells them. They actually makes a mix-up hodgepodge of triangle rule and parallelogram rule, starting the component vector set from the same point, completing the figure as a triangle. This is the most common mistake that the students do, which you should be careful and not do in the actual exam. If you're starting the component vectors from a single point, you should remember in your head that this should look like a parallelogram. This is a quadrilateral that I'm drawing. If you're placing the component vectors one after another, they should look like a triangle. This is a triangle that I'm drawing. So do not mix those up. If you mix them up, you are going to be very frustrated with triangle rule. Vector diagrams are practically very simple if you get the hang of it. But if you start making mistakes, not understanding the concept properly, then you are going to be in trouble. I mean, it's going to keep on looking more and more difficult. For many of you, geometric drawing itself is a pretty difficult thing because you don't get to practice it a lot for your math syllabus. But here you have to do that. You have to be able to do that. Oh, we are using 60 and 49 because that is the question that I came up with. I could have had any other values as well. It depends upon the question. তাই বুঝছো? ওকে, সো এটা হচ্ছে আমাদের ভেক্টর ডায়াগ্রাম। সো আমি এটা তোমাদেরকে পড়ালাম, এখন তোমরা দেখো তো এই কোশ্চেনটা সলভ করা যায় কিনা। You can use your ruler onto the screen to judge this question because you don't have a paper copy of this thing. Which one do you think is the correct response for this thing, for this resultant? I have one response from one of your classmates. Anyone else wants to care to give their answer? You are allowed to be mistaken, kids. Please attempt the question, use your understanding, and there is no problem making the mistake. No, it's not left. I mean, there are 4 options, A, B, C, D. You have to give which of the correct option is. No. Here's it. That's it. Force X and force Y act on a block. So these are the two are the component forces. Together they would produce one resultant which should be chosen among A, B, C, D. Okay, we're getting a couple of more responses. Anyone else? Mustahsin, Nurzahin, Dipro. Okay, let me help you solve this thing. For those of you who have a ruler with you, if you hold your ruler with the along this, then you should see that all the forces endpoints, all the results endpoint, which means A, B, C, and D, have these things, which means if you try to assume a parallelogram, because we are trying to get a parallelogram that should be produced by X and Y. These are the two forces which are starting from the same point, so we are trying to get a parallelogram. This side should be parallel. What is left is to find out the parallel side, which should be starting from here, going upward left. That should be parallel with the side X. Now, if I try to join these lines as best as I can, you should be comfortably saying that C or D are not parallel to A. Do you see that? Now, you might not be seeing it, even just by looking at it. There is an easier way. One of the properties of parallelogram is that the opposite sides are equal in length, right? Koloman?
Yes, sir.
Equal in length. So how about you measure this side? Take up your ruler, put it on the screen of whatever device that you're using, measure this up. This can have different length for the individual of you, doesn't matter. Then start to measure from this end to find out which point do you land upon to at that exact length. Where do you land?
Sure, B.
You should land on B. Because if you have this triangle, let me complete this drawing with black. This should be your appropriate correct parallelogram, this black parallelogram, where you have this length exactly equal to this length, and obviously this length is also perfectly equal. This length is also perfectly equal to that length. Any other option is not acceptable. Now, it is not essential that you just have to look at it and pick up your decision. There are multiple different ways you can judge the correct answer by measurement. So one way is that you can observe for the length. The other way, if you really want to go for the consideration of parallelogram, you can take up one ruler and put it across this thing. I mean, is there a way to rotate this ruler?
Sir, scroll wheel.
Eh?
Scroll wheel দিয়ে sir.
কি দিয়ে?
Scroll wheel.
Oh, thank you. So one of the other ways that you can actually check whether which of these lines is actually parallel, you can hold up your ruler, whatever thickness that your ruler has, hold it up against X, and then slide it evenly to the right side, and wait till your ruler reaches the endpoint of X, and then you should see what is the endpoint over here. Now it's important that you should be sliding it evenly, not with as you slide it, you shouldn't make it angle. That should also give you that answer to SB. So I'm giving you multiple different ways to judge which is the correct answer. But do you understand all of these procedures? বুঝা গেছে সবার?
Yes, sir.
It's a very simple question. You can have a look over here. There is no mathematical calculation. It's just a question of judgment. So if you know how to work out this math, these questions can really save you a lot of time, and you can get pretty much free marks. I mean, nothing is free, but you get what I want to mean. Okay, this is a good question. Have a look over here and see if you can come up with an answer for this question.
Sir, what is meant by turning in a horizontal circle?
What does it mean?
Yes, sir.
Turning in a horizontal circle means, let's say, it is going around a certain part of land and it is going above a certain part of land while being parallel with the ground. So it is not changing its height from the ground. It is maintaining the same altitude, but it is going above the same piece of land. Okay. The reason you might be confused for this question because I did not actually teach you about circular motion. So this is where the circular motion discussion comes in. It's 9:31. Okay, I'm gonna just go over this topic and then we might call it a day. তোমাদের সিলেবাসে সার্কুলার মোশন নিয়ে খুব ছোট্ট কিছু ডিসকাশন আছে। সার্কুলার মোশন, first of all, we're gonna see objects which has uniform speed. I might as well write constant. এই তিনটে ইনফরমেশন তোমাদের সিলেবাসে আছে। So the idea is very simple. Let's say we have an object that is going around in a circular motion. I'm not saying vertical circle or I'm not saying horizontal circle. Let's say an object is going around in a circular motion where this is the center of the circle. You have to understand, even if the object maintains uniform speed, its velocity will be continuously changing because at any point of motion, the instantaneous speed would be tangent with the circle. This is the instantaneous speed. So instantaneous velocity, why am I saying speed? Instantaneous velocity would be tangent with the circle. So after any amount of duration, let's say whenever the object travels from this point to this point, even if the object has a constant speed, it would have a significant change of its angle. So this angle, this vector is aiming this way, this vector is changing this way. So there is a change of direction. That change of direction also brings about a significant change in the velocity, because velocity is a vector quantity. So change of velocity can happen by the magnitude change, by the direction change, or by the simultaneous change of both. So that change of velocity is resulted in from an acceleration, or I could say the other way, there is an acceleration which causes the change of velocity, and that is called centripetal acceleration. For circular motion we call that centripetal acceleration, which always works towards the center. A very simple example that can help you to understand the idea of centripetal motion is that if you have in your hand a stone that is tied with a piece of rope and you start to swing it pretty fast above your head, what you'll find out that as long as you keep rotating this stone with your hand that is stuck with a rope, you'll see that the rope is always taut. For any motion, the rope is actually never getting slack. The reason is that practically to make the stone go around our hand, we basically pull the stone towards the center. And just to make sure that it does not fall down, we have to move our hand a little bit in a small circular motion so that we can keep on giving the object a bit more energy so that it doesn't lose its height to overcome the air resistance. That's why you have to move our hand. But if air resistance was not present, then we would not need that additional force. For example, the motion of Earth around the sun is almost circular, which is it's not perfectly circular, it's slightly elliptical, but it's almost circular. But that's an example of a constant speed but changing velocity of motion. Earth goes around the sun in 365 days, so it covers a huge amount of it covers 2 pi radian angle or 360-degree angle with the sun's center in 365 days. So it undergoes a significant amount of duration change over this duration, and the gravitational pull of the sun actually causes the Earth to go around this change. So this is the scenario what happens for circular motion. A couple of information once again. For your syllabus, we're going to only see objects with uniform or constant speed. Centripetal acceleration causes this circular motion, which comes from centripetal force. Any object that undergoes circular motion, no matter where that is, in general, we call the force that causes the circular motion to be centripetal force, and the acceleration to be centripetal acceleration. The source of that force could be different. For example, for a celestial case, gravitational force works as a centripetal force. If you consider the structure of an atom, we have a positively charged nucleus, we have negatively charged electrons on orbits. In that scenario, electrostatic attraction force, the attraction between opposite charges, plus and minus charges, that works as centripetal force. For the case of the example that I was giving, that string attached stone is being rotated above our head, in that case, the pull of the string, tension of the string, tension is the name, tension of the string is causing the centripetal force. So the factor or the source from which that circular motion causing force is available can be different. But in general, any force that causes an object to go in circular motion, we call it in generally centripetal force, and it always works towards the center, but the instantaneous velocity works tangent with the circle. So basically what is happening at any point of motion, the force is working this way, the velocity is working this way, the force is working this way, the velocity is working this way. And this is also why any amount of work done in circular motion is always zero, because work done is given by force multiplied by direction, distance moved in the direction of the force. And in a circular motion, the object never covers any distance in the direction of the force, because the force always changes direction and the object is also changing velocity, so that they're always 90 degrees to each other. So the object simply is not getting closer, not getting further away. So the amount of net work done for a circular motion will always be zero. So that's another concept for the work energy power chapter, but that's basically what you have to know for circular motion. You can have questions. I appreciate questions. If you have, please write them down or send me your questions in my messenger directly. For today, I'm not taking any more questions. Thank you for the additional 9 minutes of attention. We'll pick up more topic next class. আর এর মধ্যে তোমাদের বাসার ঠিকানা আমি অ্যাড্রেস পাঠাতে ব্যবস্থা করছি। তোমাদের একটা ফর্ম ফিল আপ করা লাগবে। আমি কিছুক্ষণ পর তোমাদের বা কালকে কালকে আমার ফর্মটা একটু এডিট করা লাগবে। কালকে তোমাদেরকে আমি একটা ফর্ম ফিল আপ করার একটা লিংক পাঠাবো, তোমরা একটা ওয়েবসাইটে গিয়ে আমাকে ফর্ম ফিল আপ করে দিবা। I'll have the addresses in my email directly from that website. We don't have cookies enabled, so you can go there without any problem. I hope we don't have cookies enabled. No, as far as I know, we don't have cookies enabled. Anyway, and then I'll get your addresses and I'll try to parcel those things to your address, and I'll also share the payment mechanism with your kids for those who don't know it. And yeah, our next class will be on next Wednesday. Thank you very much. Eid Mubarak.
Assalamu alaikum, sir.
Walaikum assalam.